Hey, welcome everybody. I think we've got 1 minute and then we'll start. Okay, we'll get this started. So welcome everybody. My name is Scott Kuhlman. I'm the co-founder of ReCircled and ReCircled Consulting. Um, Thank you for being on. I know here in the US, as just pointed out, we've got lots of competition today with other things happening in our country, but this is obviously just an incredibly important issue. As most of you know, at ReCircle, we're working on processes and finding ways to take care of all the articles of clothing and footwear and handbags and so forth. And we're pleased to have Jesse Daystar and Joe Sagues from North Carolina State on with us today. I'm going to let them do most of the talking, as a lot of the things they're going to talk about are new, and we'll just jump right in with it. So Jesse, and by the way, Jesse's with Cotton Incorporated, so I'll let him say more, but I'll let you take it away.
Great. Thank you so much, Scott, and thanks for your team and everybody hosting this. We're glad to come together today to talk a little bit about some opportunities in circularity and cotton, and particularly capturing carbon from the carbon cycle. So, all right, looks like the slides are up. So, a little bit about me. My name is Jesse Daystar. I'm Chief Sustainability Officer at Cotton Incorporated. Cotton Incorporated is a research and promotion group located in Cary for the cotton industry. And our goal and mission is to improve the demand and profitability of cotton through research and promotion. And sustainability and circularity is definitely key to both the promotion as well as the profitability and ultimately sustainability of cotton as we look to the future. So yeah, next slide, Joe. So here's a picture I took on the coast of North Carolina, which I'm located in, that kind of sums up in some ways the take, make, waste linear system where plastics and many products in this world really, go one direction. They have an ability to stick around in the environment for very long periods of time and create waste, and we're not capturing that value, pulling materials back into our systems to capture value and make new products. And we've all seen stuff like this in our world, and we know it's a common problem. Next slide. It's definitely becoming a growing issue in the apparel industry, where we're seeing from space piles of clothing and the Chile deserts, which is what this is a picture of. So we're able to see textile waste from space, and millions of tons of this is certainly just getting out there in the world and causing impacts to the environment, impacts to people, and clogging up our ecosystems. Next slide. A couple of years ago, actually about 2019, we started a project with Qantas and some leading scientists around the world to actually put a number to the problem, to look at what is the plastic pollution or plastic leakage rather that is getting into the environment. And plastic leakage is essentially plastic that gets into the environment like that bottle in an unmanaged way. If you recycle that bottle, that's not leakage. But if it winds up on the ground or a straw in a turtle's nose, as we've all seen, that's plastic leakage. So we wanted to get a global assessment of how much plastic is getting into the world from the apparel industry. And that kind of gives us a bearing of, what is the size of this problem, particularly as it pertains to a linear system. Next slide. Well, it turns out that 8.3 million metric tons a year, or around 14% of all plastic leakage, is comes back to the apparel industry. So the apparel industry is responsible for a significant portion of the plastic leakage in the world, and 13% of the total plastic leakage actually is goes back to synthetics, the use of synthetics, and particularly the end of life, or what happens to the synthetic clothing when we're done with it. A lot of times it's shipped to those deserts in other countries, for example, and is in an unmanaged way. A lot of material is done that way, and that creates a big portion of plastic leakage, which is, as you can see here, 9 times the Golden Gate Bridge or 23 times the mass of the Empire State Building, just in other terms, because it's such a big number. It's really hard to really grasp the size of this problem. Next slide. This is a common diagram used, but to kind of describe the two different systems we have and ways in which we can think of products and whatnot. You have a natural system, which is renewable, using carbon cycle and renewable resources on the left-hand side. And on the right-hand side, those are fossil-based systems. And you treat and look at these things different ways depending upon which side of the fence they're on there. But overall, you try to retain the value of any product or material you have as long as you can, and trickle that down appropriately through time, as that product will usually degrade. Next slide. Another thing to consider too, like recycling is almost synonymous with circularity. And in reality, it is an option potentially amongst the circularity paradigm. However, when you look at the actual life cycle assessment, which is one of my backgrounds, I did that in my PhD research, or measuring the environmental impacts of product, services, or good. It's kind of environmental accounting. When you use this framework to look at, is recycling better? There are studies out there that show maybe just growing virgin cotton, and because it already has a low carbon footprint, making a quality product that's durable would have a lower impact than recycling, particularly when you start to think, well, what else could we be doing with the waste clothing? Could you turn it into insulation? Or maybe the point of this conversation, biochar. There's a lot of options you can do with that material that capture that carbon for very long periods of time. So you really have to think about, is recycling the best option? Certainly it is an option, and that can exist, but there's far more other options out there that might make a lot more sense in terms of sustainability and carbon capture, profitability, and making products that people want and are going to last a long period of time. Next slide. Another thing that really is unique to cotton, that say synthetics and a lot of other materials don't have, is that we are actually circular from a nature perspective. To grow cotton, or a tree, which cotton actually is a tree, it pulls in CO2 from the atmosphere through photosynthesis. It pulls in CO2 and kind of puts out oxygen, which is real convenient for the world. And as we pull in CO2, we harvest that cotton. If you're wearing cotton right now, which I hope you are, you're actually wearing CO2 that was once floating around in the atmosphere. It's warming you instead of the environment, which is pretty cool. Well, what if we could take that carbon from your closet and get it stored for very long periods of time, making it so that it doesn't go back to the atmosphere? That could really create a large benefit of having the plants do their work, pulling the carbon out of the air, getting a first use out of this material that we all want to do, and taking a waste product and capturing carbon for long periods of time. There is a market for that, particularly carbon inset market, that is very interesting. But beyond that particular point, cotton and agriculture can actually capture carbon in the soils and throughout other means of their life cycle as well. Next slide. So at Cotton Incorporated, we see a need for realistic, scalable circular solutions that actually reduce the environmental impacts. We need to look at this first and foremost. Is this going to help the environment? Let's not do it for sake of doing it. Let's really drive towards solutions that are going to drive down carbon emissions and improve the environmental profile of cotton and the apparel industry. Next, is it economically viable? Is it a pie in the sky thing? Does it make sense from a business perspective? Is the incoming material going to be 3 times the price for the garment producer, or is this going to be really competitive with other options? Next, is it something that is simple enough to scale, or is it so complex that the capital and the technology isn't ready? That's like a 20-year out pie in the sky thing. While it certainly is room for innovation, we need to really look far out. We can't ignore the now and the needs of the present, because if we don't solve some of the immediate pressing issues, the future is going to be in a far worse place. So we have to consider this in perspective. And finally, what are the gaps in the industry? We at Cotton Incorporated don't want to be redundant upon private enterprises, exercises and the things that they're doing in their place. So we're looking at kind of other areas that are a little bit more new and novel that we see great opportunity, but we're not being redundant to private industry. And over the next few slides, we're going to go into a few of those. Next slide. One thing which we've had great success with is the Blue Jeans Go Green program, where we're actually working with different companies to have consumers and different collaborations collect jeans, and we actually turn it into insulation that you can buy and put in your walls. It has really a lot of great features from a material perspective, but the main thing is you're taking carbon that was once in the air, you're wearing it in your jeans, and now you're putting it in your wall, which can keep that carbon stored for a pretty long period of time. Maybe a house is 50 to 100 years, so you've kept that CO2 out of the air for a significant amount of time, as well as you made the house more efficient. And consumers and brands have been working with this program for a long time and have collected, this is over almost 2,000 tons of jeans at this point. Next slide. Another area, probably just go ahead and click through all these, Joe. Yeah, that's it right there. Another area which we're looking at is, can you take clothing, break it down into smaller pieces, and treat it with some different chemical processes using enzymes to break it down to its actual more fundamental chemical formula, in this case, into a glucose. You can use enzymes to take the celluloses, which cotton is made out of, which is a number of sugar molecules like we would eat, but connected through a beta-O4 linkage to create a more complex linked sugar molecule. So if you can chop that up and break the cellulose down into individual sugar units, that can be used for a lot of other materials as a chemical intermediate, which would maybe normally come from petroleum-based products. Now you can use that as a raw material to make a variety of products. And we're looking at that for cotton. And we've got a couple of patents and ongoing research in which we're really trying to figure out, could you take maybe cotton and even mix cotton with other materials and use enzymes to extract the sugar and go forth with that as an individual product, and maybe extract the synthetics and do something else with them, which is a neat approach to this. So we have ongoing research in this area that is looking pretty promising. Next slide. Another thing which we're pretty excited about is composting. It seems, maybe a little too simple, but when you start to look at it, there's something there. Simple but effective can be, a good solution that is more near term and scalable. And, composting is a controlled biodegradation, kind of an engineered system which solves a waste problem, can improve nutrient profile in soil, and capture and enrich the soil carbon content as well. So there's some different variety of benefits there, as well as just, it solves a waste issue. Next slide. So we actually set out with Cornell to look at, could we compost jeans that we just bought off the internet, brand new jeans. We got a variety of different ones, but this one here is 100% cotton. We buried them composted them in the windrows. And after 1 month, you can see that significant degradation has occurred. After 2 months, a lot more. And really all that's left over at the end is going to be the pockets, and anything that is not cotton, that's not natural fiber, that's going to stick around, because we've shown through various research publications and, kind of your eyesight, we all know that plastic doesn't really biodegrade. So we've shown that cotton can biodegrade in the composting environment. Next slide. We contrasted that with a pair of cotton and poly blend jeans that I think was about an 80-20 split. About 20% of it was polyester. And while the cotton did biodegrade, it left behind the polyester skeleton of the jean and all that plastic that just couldn't go away in that condition. So, it's really a visual of, showing that cotton is, if left to its own demise in nature, is going to biodegrade, and polyester and plastic and synthetics just don't really have that feature that is designed into the world to make cellulose and natural materials biodegradable. Next slide. Another area we're looking into, which is sort of counter to the last idea, I was just talking about how we can use cotton to biodegrade and enrich soils. But what if we flipped that on its head and said, well, what if we could keep cotton from biodegrading? What if we could stop that and, again, capture that carbon for long term? There's a company called Graphite that is actually doing this with forest residues, or kind of waste forest materials after logging and such things. They're pelletizing, or they're making it into briquettes and burying them in a controlled way that keeps the carbon locked up for long periods of time at a fairly low cost, and in a way that has pretty good certainty of longevity of that carbon capture. Well, we're now going to be looking into that for cotton. Could we make these into bales? Could we bury them in a controlled way, which would help ensure that carbon is captured? And as carbon is captured, there's companies out there, whether that be an apparel brand or maybe a Microsoft or other companies out there, that are willing to pay to pull carbon out of the atmosphere. Well, this could be a viable solution that really could pull a lot of carbon out of the air, solve a waste issue, and really leverage the advantages of cotton and the overall carbon cycle. Next slide. But today we're going to dive a lot deeper into, could we do this with textiles? Could we turn waste cotton and cotton textiles into biochar, which is using a little bit of technology, as Joe will go in more detail, and turning it into something like charcoal or coal that's made from natural materials that's going to hold that carbon for a long period of time. And there are, a number of benefits potentially to, land application, agriculture, and even battery storage, which I will get into. So this is a new exciting area that really fits into our overall theme at Cotton Incorporated as to how can we leverage the natural carbon cycle and improve the environment and do something that is in a scalable, profitable way that's going to really help sustainability, really help cotton, and be something that we can do in the near term. So with that, I'm going to go ahead and pass it, I guess, back to Scott, then to Joe.
Yeah, awesome. Awesome. Thanks, Jesse. Really appreciate that. Hopefully that gave a great oversight for everybody. First of all, on the right-hand side of your screen, you'll see a little question mark. You can ask questions there. When we're done, we'll go back through those. And also we have a couple polls over there. If you can see, I think the number 2 is up right now. If you could answer those, will help us with what we do next. So with that, I'll turn it over to Joe and we'll dive into this, the idea of biochar.
Sounds great. Let me just get things set up here. All right. Okay, assuming that looks good. So I will jump right in. Thank you, Jesse, for that great overview of the various opportunities for enhancing circularity, as well as addressing the climate issue through the textile industry, specifically with cotton. As Jesse said, I'm going to focus more in on biochar as one opportunity that we're particularly excited about, right? Because I do think there's tremendous opportunity to create value and, importantly, remove carbon from the atmosphere. And so I'm an assistant professor at North Carolina State University in the Biological and Agricultural Engineering Department, and I'm a principal investigator of the Biocarbon Utilization and Sequestration Lab, where we try to develop innovative bioprocessing, biomass conversion technologies to remove carbon from the atmosphere. And quickly want to thank Jesse and Cotton Incorporated for funding the work that part of the work that I'm going to present today. So I want to start off with one of the primary motives behind this work, which is, as Jesse's already spoken to, the need to begin removing carbon dioxide from the atmosphere in rapid fashion and at very large scale, almost inconceivably large scale. So I like this metaphor, which is basically thinking of our atmosphere as a bathtub, right? And for the last 150 to 200 years, we've been pouring carbon into our atmospheric bathtub at an increasing rate, right? Now we're at close to 60 billion tons of CO2 per year. We've got about 3 trillion floating around in the atmosphere. And the problem is we need to turn this valve off entirely, but that's turning out to be very difficult. And most experts believe, including the Intergovernmental Panel on Climate Change, we might be able to close this valve like 80% of the way, maybe 90% if we're really good at electrifying and whatnot. But there's still going to be some fossil emissions, some methane and nitrous oxide from agriculture. And there's also going to be legacy fossil emissions that are just stuck in the atmosphere for hundreds of years that will contribute to warming. And so we need to begin draining our atmospheric bathtub as a means to address this climate issue, right? So avoiding emissions, great, but also removing emissions through the drain is what we need to start doing. And that's called carbon removal. And so, a question I like to pose to the audience is this linear or circular? And, it's technically linear, but it's in the reverse direction. So it's got tremendous benefits, of course, but it is technically, if you're looking at greenhouse gases, it is a linear process. But that's not to say that the various carbon removal solutions that are being developed are entirely linear. There are certain attributes that abide by the principles of circularity. And I think biochar is one good example of that, which I'll touch on the various circularity impacts, but the majority of the talk today will be on this carbon removal to address the climate issue. Another motive, which is of course really important if you want to scale these things, is the monetary value in removing carbon. And so there are voluntary in the US, it's mostly voluntary. Actually, in the state of California and Oregon and Washington, there are actual policy mandated markets now that allow for trading of carbon removal credits, but most of it's voluntary and most of it is driven through large tech companies and large banks for now, as they need to decarbonize their massive expanse in AI and data centers. They're turning to carbon removal and they're turning to biochar, which I'll get to in more detail in just a moment. But you can see it was about $3 billion in 2023. It's growing at a rate that should exceed $100 billion sometime before 2035. Microsoft, I think, is an interesting example because they not only want to go carbon neutral, they want to remove all of their historical emissions. So that over the history of the company, starting in the 70s, they're going to be carbon neutral, which I think is really neat. And so the vision here in my lab and something that Jesse and I, as well as Scott, are in alignment on is, the bioeconomy has a fantastic opportunity to become carbon negative. Right? And so this is showing a simplified schematic of the various operations along the supply chain in the bioeconomy, which processes basically biomass, including cotton, right? So of course, as Jesse mentioned, when cotton is being grown and other types of biomass, that's sucking carbon out of the air, right? And then throughout the supply chain, there are various emissions shown in the orange, but there are also various opportunities to keep this carbon in out of the atmosphere, whether that be in the ground, deep underground, in the soil in the form of biochar, which is the focus of today, or the products themselves can be very stably buried, whether in a landfill or other means like biomass burial, like Jesse talked about briefly. All right, so the goal is to have the sum of mass in the green arrows be larger than that of the orange arrows, so that on net, you're removing carbon from the atmosphere through bioeconomy processes. Let's get to biochar, okay? Now, biochar is made through a process called pyrolysis. Okay, biochar is a solid material. It looks a lot like charcoal, like you would buy at the store, but it is different in the fact that it's typically more porous, and it's made through pyrolysis and not incineration. Okay, so it's a solid carbon-rich material, highly porous, non-reactive. It's produced from pyrolysis, where biomass, which includes cotton textiles, is thermally treated at somewhere between 400 and 700 C in the absence of oxygen. Okay, a lot of these processes are autothermal. They don't need external heat input. They kind of self-regulate themselves, but it is not burning. You are not incinerating it. If you were incinerating it, the majority of the carbon would be converted to CO2 and go right back to the atmosphere. Right? Through pyrolysis, a majority of the carbon is converted to this stable carbon material shown here. Right? And since it's very inert and non-reactive, it allows for carbon sequestration. And so another important motivation here is the demand is growing for biochar and activated biochar. Activated biochar is basically taking biochar and doing a chemical treatment at high temperature to make a very, very high porosity, high surface area material, which is higher value. But most of the growth is the sort of traditional biochar. You can see in 2023, we're at 0.7 billion. It's gone up to, it's growing at 14%. That's the important part, right? So if it continues this trend, it'll be in excess of 2 billion by the end of this decade, approximately. The primary application is in the ag sector, and that is in large part due to the trading of carbon removal credits that is possible through the application of biochar in soil. And there are some agronomic benefits to the crop by adding biochar, which I'll get to towards the end. If you look at activated carbon, it's a larger market, higher values, but it's not growing as much, but it is growing, and it's primarily used in water treatment, air filtration, and energy storage. So last week, just a few days ago, there was an announcement. This is just one example of a recent commercial development here, but Google has an offtake agreement to purchase 100,000 tons of carbon and biochar. I don't remember the time span, but it's in short order, right? So they're going to be making this biochar rather quickly, which means large scale, right? And so this is just one example of a company named Charm, who is working with major corporates to help decarbonize their supply chain, their emissions through the production and application of biochar. Okay, the last motivation here is around the growing problem of textile waste. In the US, there's over 10 million tons landfilled each year. If you were to quantify sort of a ceiling in terms of what could be removed from the atmosphere, that correlates to around 22 million tons. Right? Assuming a price of around $150 to $200 per ton CO2 removed, which is actually a pretty conservative price for what carbon removal credits are going for these days. That's in excess of $3 billion in revenue just in the US. Right, so there's a missed opportunity in our view to valorize this biogenic carbon in cotton instead of just landfilling it. And to get to Jesse's point, if you were to recycle it and convert it back into textile, that is, of course, a great circular approach to dealing with the waste. But does it create as much value? Right? What are the returns, and also what are the impacts in terms of climate impacts and other environmental impacts, as opposed to making biochar? Right? There needs to be more work into investigating that. And then finally, PFAS and other things that are in synthetics are a growing problem, of course. And the nice thing about pyrolysis is that it degrades these nasty PFAS and other types of pollutants that can be really detrimental to human health. All right, so just to give you sort of a snapshot of what this looks like at a high level, right? Doing a little bit of mass flow, mass balance, right? Starting with the carbon in the atmosphere, of course, it's taken up by the cotton during its growth. That cotton is then sent to manufacturing and finally manufactured into textile products, which are distributed to consumers, right? And so you have these different waste materials down here: field level waste, pre-consumer waste, and post-consumer waste, right? All of which contain significant quantities of cotton or biogenic carbon, right? And so the idea here is try to find these, whether in centralized, uniform sources or more distributed, heterogeneous sources, and see what can be done to convert them into biochar at relatively low cost. And then after that, of course, you've got a number of different applications and markets you can sell the biochar into, with the soil application, of course, growing at the largest rate. But in my lab, I do quite a bit of work of taking biochar and putting it into batteries. And the Department of Energy has funded my group on a number of grants to look at using biochar in lithium-ion battery anodes. So I'm not going to talk about that today, but that's another area of a lot of interest to me. Let's talk about soil for a moment. Okay, so starting with this plot on the right here, this is a collaborator of mine, Dr. Alex Woodley, in the soil science department here at NC State. And these are real plots. That's a truck right there. These are real plots in eastern North Carolina, applying biochar primarily for the growth of corn. So not looking at cotton, and also not using biochar derived from cotton. This biochar, I believe, was mostly from pine. But nonetheless, it shows you, at NC State at least, we have the ability to perform these large trials. And he has not published these data yet, but there are plenty of other trials out there showing like biochar in soil can be highly beneficial. Why? It can sequester carbon for one. It can reduce erosion and runoff. So these are kind of co-benefits that come from biochar application. It can decrease the loss of soil organic carbon, or priming as it's called, the technical term, which is great because that even further helps with carbon sequestration. It can reduce nitrous oxide emissions. That's a third benefit, at least to the climate, right? N2O has a warming impact about, over 200 times that of CO2. So it's a very potent greenhouse gas. And you can increase your crop yields. There's data showing that's possible. Right? So what are important properties to look at in a specific biochar material? Right, so there's a few things. The yield, which is basically how much biochar is being produced per unit dry weight. So how many tons of biochar are made per ton of textile waste, for example. The surface area, which is basically when you zoom in to a biochar particle, there's all these pores, right? And all those pores have surface area on them, a remarkable amount of surface area, right? The more surface area, the more ability it has to retain moisture, to resist degradation, to allow biofilm development, which can improve soil health. And in general, the more surface area, the higher quality. The morphology, basically, what does it look like? And I'll show you some images soon. And then the carbon content, right? The higher the carbon content, the better, because that means it's sequestering more carbon and it's more stable. So that leads to this research question, which Jesse Daystar very graciously funded my group to look into this, and we're going to continue the work over the next year or two. Can cotton textile wastes be converted to high quality biochar, right? That's really kind of what we set out to look at. We went further and looked at the applications in energy storage, but I'm not going to be showing those data today. I'm just going to show you kind of like the general characterization data. And I will try to move pretty quickly. And some of this is technical, I'll say up front, but I'll try to point out just the really important parts. And so looking at how we did this, we took 3 different textile materials: pure cotton, a blend of 50-50 cotton poly woven blend, and then pure polyester textile materials, right? And we treated them at 3 different pyrolysis temperatures, 400, 500, and 600 C. Held them all for 60 minutes. We carried the reactions out under nitrogen, so it's an inert environment. And then we took those materials and activated them as well in the presence of potassium hydroxide to make activated biochar. This is the more technical slide, so just bear with me for a moment. I'll point out the things that I think are important because these materials, the three textiles, right? Pure cotton, cotton poly, and pure poly, they do react differently during pyrolysis. And the way we're able to distinguish this is through what we call thermogravimetric analysis, which measures the change in a material's mass as a function of temperature to understand thermal decomposition. And so on these 3 plots, we've got the mass of the textile material as it changes with time, as it changes with temperature on the x-axis. The temperature is increasing, right? And so you can see this curve, right? The blue curve begins to decrease at around 300 to 400 C, right? So that's when the pure cotton material is degrading rapidly. This green peak here is showing the rate of change. So the rate of change is the highest at around 363 degrees Celsius. Okay, let's look at cotton poly. The thing to take away here is that there are 2 peaks, which means that there's decomposition happening at approximately 360 degrees C, but again at around 440. And so that is basically correlated to the cellulose or the cotton fibers decomposing at this range, and then the polyester fibers decomposing in this range. So 2 different decomposition temperatures taking place. And then finally, the pure polyester, you can see there's only 1 decomposition happening at about 440 C. Okay, and that's not surprising, 2 different materials, but we're able to see quantitatively how the material is changing. Now let's look at yield and surface area for the 3 different materials, right? So the yield, again, is how much biochar are we producing relative to the starting mass, right? The starting textile waste. And so at 400 C, we're getting about 20% yield. So if you had 1 ton of textile waste, right, you would make 0.2 tons or 200 kilograms of biochar. And then at the higher temperature, it goes down, right? But overall, the yields range between about 15 to 20% for all 3 materials and all 3 temperatures, which is what we roughly estimated we would see. What we did not expect is that the surface area changes drastically. So starting with pure cotton, 400 C, very low surface area. At the higher temperature, we get 350 meters squared per gram. But interestingly, the cotton poly blend, even at low temperature, we got over 550. And that values over 500 typically are for activated materials. And so this was a really unique phenomenon which hasn't been published before. We're really excited to see this because it's a very mild process. We're getting really high surface area, high quality biochar, much higher than the pure poly, right? And so what this is saying is there's an interesting phenomenon taking place between these 2 materials as they pyrolyze. Very quickly, I just want to show you some morphological changes on a macro scale, just taking pictures basically through a Ziploc bag of the starting material, the 100% cotton, and then the final material. And it's a little low resolution, my apologies for that, but the main takeaway here is that the fibers are retained and you actually have pretty good structural strength and form after pyrolysis. For both the pure cotton and also the cotton poly blend, we're also getting like a nice solid structure after pyrolysis. Whereas when you do the polyester, it comes out of the furnace and it's crumbly, it's very glassy, it's a very different type of material. And we can see that in the scanning electron microscopic images here, where we've got the 100% cotton, the blend, and then the pure polyester, right? And we're using a microscope to zoom in to a scale of 500 microns, right? Really small scale, half of a millimeter. And what you can see on the cotton biochar is all of those fibers are retained, right? This is after pyrolysis. We've got all of these biochar fibers. For the blend, you can see a little bit of the fibers, and they're kind of melded together with the polyester. And then the pure polyester was a glassy material, no fibers left over. And this is more obvious when you look at an increasing magnification. So zoomed out on the left and then moving in closer and closer on the right, we can see those fibers with the pure cotton material very clearly. And then with the blend, as you can see really in this image here, you can make out the cotton fibers and they're melded together with the polyester. And so our hypothesis is that during pyrolysis, right, we've got these two different decompositions taking place. At this first decomposition, the cellulose is turning into a gas. The fibers are being converted into a gas, and that gas is being trapped in sort of a molten polyester, right? And so, not to get too technical, but we think there's these small pores forming in the molten polyester due to the decomposition of the cotton fibers, making this really unique material. Lastly, I want to touch on the activated biochar. So we take the biochar, we then treat it with potassium hydroxide. It's a very standard procedure. And the surface area is now increasing drastically, which we expected. But what we didn't expect is the significant increase for the pure cotton. So we went from about 200 to 300 meters squared per gram up to 2,500. Right, so that's a 10x increase in surface area through this treatment. So that's really high quality activated biochar. And we saw a pretty good increase with the cotton poly blend as well. Not as high, but exceeding 1,000 meters squared per gram is great. And especially when you compare this to what you see in the literature. So coming to the end here, I wanted to just quickly show this slide that is concerning some ongoing work that Scott has got going on with this company called Biochar Now. And Biochar Now and Scott sent me some of their biochar from textile waste, shown right here, right, which has a very high carbon content, which is really rare. And it speaks to the novelty of the Biochar Now process, but also the textile waste, I think, has just good attributes for biochar production. And so I'm really excited about this project that Scott's leading. And you can see these reactors are not that complicated. They're made of I think, just plain carbon steel. And they're basically furnaces that make biochar quickly. So scalable, modular, but scalable, which I think is pretty neat. So just to come to a conclusion here, right? Biochar and activated biochar markets are growing. The cotton polyester textile provides a high surface area of biochar material at modest temperature due to that unique phenomena that I discussed earlier during the decomposition or during the pyrolysis. Other applications should be investigated for the cotton poly biochar, water treatment, nutrient recycling, air filtration, etc. Also energy storage. Cotton textile provides a high surface area, activated biochar. So when we activate it, we find that the 100% cotton material looks really good. Field level studies are needed. I think Scott's already kind of getting the ball rolling here, but we need more data from the field level, putting biochar into the soil to look at the efficacy and permanence of the biochar. And then finally, looking into the techno-economic and life cycle assessment to really understand the commercialization potential. And as Jesse mentioned, him and I and our team at NC State does a lot of this for various biomass conversion processes, including pyrolysis. And so with that, definitely want to thank you for your time. This is my group here. I want to acknowledge Cotton Incorporated and Jesse. And then a final little plug to my lab, the Bus Lab here at NC State. We've got a number of different furnaces and pyrolyzers to make biochar of all types, starting from all materials. So if anyone wants to collaborate with NC State, please shoot me an email. With that, I'll stop sharing.
Awesome. Thank you, Joe. Thank you, Jesse. We do want to open this up to questions. I think I've tried to answer all of them. Jimmy, to your question on water filtration and removing forever chemicals, biochar, and again, Joe or Jesse can speak to it. We've literally been doing some research on it. For the fashion industry, just last week, we discovered that there's an issue with silica gel packs. We learned that silica mixed with biochar is an incredible way to remove heavy metals from water. There's a process, and it's something that's being done, particularly cadmium, where cadmium is present. So there's a lot of work being done around that. And by the way, yes, we do have email addresses we can get. So if we don't get everything answered, you want to reach out for more. Joe and Jesse have been great about getting information out. This is way too important for not everyone to know about it. So with that, if you have questions around this at the moment, please let us know. Amir, are you just having it go through chat or through the questions, or will they actually jump on?
They're able to post their questions to the chat.
Okay, yeah. So either through the chat or through the actual question side of it, we're happy to answer them. So the question was, are you, Madison asked about, are we looking at other textile blends? I think that was answered with Joe mentioned that he studied both cotton polyester, as well as 100% polyester. We are now, with the results of these, starting with other things like wool, etc. We're going to see some research very shortly and very quickly on that. So we'll hopefully be getting that out to you. Our thesis is obviously with wool. It's a biomass, so we're probably going to see some great information or results from it. We're not worried, but we're excited about too are these blends, as we're trying to keep expenses down and produce a process that creates revenue so we can pay for all of this. We love the idea of being able to mix textiles and not have to spend the huge amount of work with sorting and sifting and all those types of things. So we are working on developing those processes as well. Any other question?
I went ahead and put a link in the chat to a study on using activated carbon or activated biochar for PFAS removal in water. I know there was a question on that, but in general, just to follow up, Scott, yeah, usually activated biochar is more effective at treating water to remove pollutants, but biochar does have some ability due to its porosity. You just have to use more of it to kind of clean up water.
I would also encourage, as Joe was and Jesse were kind enough to put on, we are working with a company called Biochar now, who's located in Berthoud, Colorado. They have extreme experience. They also have a very unique process, as they said. You saw a picture of the kettles. The owner, who hopefully will be on a coming one, it's called Biochar Now. You can look it up. He always prefaces and says, don't believe everything you read on Google about biochar and the process. There are different ways to do it. The way that we're working with pyrolysis is time and temperature, and it's proving to be the winner for the process with textile waste, and we're continuing to prove that. So if you want to learn more, again, just reach out to us, and happy to show you. Any other?
I think Abby had a question on the SEM imaging. Yeah, thanks, Abby. So the polyester, as it's being pyrolyzed, will melt, it appears, and then it will carbonize. And so I think what's happening is it melts, right, and then kind of just encases the cotton fibers, which do not melt. They basically go straight from solid to gas phase during pyrolysis and kind of char and carbonize. And so that's why I think we see that morphology is the cotton polyester melts, kind of seeps in to all of the cotton fibers as they're pyrolyzing, resulting in that unique kind of melded look.
It brings up another subject, Joe or Jesse. We're obviously talking about the producing the biochar itself. Can you just highlight maybe some of the other things that we get from the pyrolysis process?
Yep. Yeah. So in pyrolysis, I went a little fast on that slide, right? I just wanted to first differentiate it from incineration and burning. But yeah, in a true pyrolysis process, you're generating biochar, so a solid product, but you also have a hot gas that leaves the reactor, and that hot gas can be condensed. So if you pass it through some condensing coils, a liquid will come out, and that is referred to as bio oil. And it's energy dense. It can be used as heating fuel. It can be used as a precursor to making different types of fuel like gasoline and jet fuel. It's expensive to do it, but you can do it. And there's other applications for that bio oil, even in food products like liquid smoke. What's used in barbecue sauce is a type of bio oil. And then what's not condensed, there's a third product, which is called syngas. It's mostly carbon monoxide and some other light chemicals. And that syngas can be burned to create heat and power. So there's really three products from pyrolysis: solid biochar, liquid bio oil, and gaseous syngas.
And a fourth, carbon credits. So it's
right.
Carbon credits.
Exactly. So
Yeah.
this is why we obviously are jumping in the process as we're looking for revenue to pay for all this and take care of huge quantities. And so that's why we like these multiple streams of revenue potentially from this process. So thank you for that. What other questions?
And I'll add just a little bit more tidbit, just kind of context too. Waste textiles certainly is a great opportunity. Cotton Incorporated, working with Joe and others, has also looked at other aspects of the cotton crop. For example, the gin trash, or what comes out of the cotton ginning process, where we separate the seed from the fiber. What opportunities, making sure we use all the plant material that comes out of the field as economically viable. And there's other opportunities across the value chain for textiles. It doesn't have to be one particular part. Pretty much, I think materials across the value chain, particularly as it pertains to cotton, could be used for this. And one thing that I just want to really drive home the point: if you do biochar of, say, fossil fuel-based fibers, there is no carbon credit, because that carbon was initially locked up, and you just keep it locked up. So it was never pulled out of the air within the time frame that's relevant. But when you're looking at biomass, say from wool, leather potentially, and particularly cotton, that when you biochar that, you can create carbon credits. So it's a very distinct thing there that, due to the nature of pulling carbon out of the atmosphere and keeping it out of the atmosphere, differentiates natural materials from synthetic petroleum-based materials.
Yeah, and Jesse just brought something up. Our introduction to biochar was around leather, so just know, outside of this conversation, we are working on other materials that as a fashion industry we use. Lots of great data around that we'll share as well. So Liz brought up a question: how can brands participate in using their waste to make biochar now? Thanks, great question. We simply, at ReCircled, are building the process for taking it in, pre-processing, and then getting ready for biochar. The great news is we can start today. As a matter of fact, there's a lot of biochar being produced as we speak, using textile waste from several of our brand partners. And we're open, again, we're agnostic to anyone. We're trying to solve a problem. As Joe and Jesse mentioned, we believe this process can be set up anywhere on the planet. We can do it small or we can do it big. And so that's why we love the process. So I know we're a couple minutes over. We want to, I know we can keep talking about subjects like this forever. We're very excited about it. I posted my email address. Please reach out to me if you have additional questions. I think Joe posted his as well. Again, we'd love to hear from you. Anything we can do or thoughts, happy to share all of our information, but look for continued data around this and, lots of great information. So with that, thank you very much. And just as one more thing, we plan on doing these quarterly. Is when we plan on doing these. 2025 is about thinking differently and really thinking about, are we just chasing things because we were told to, rather than are there processes out there that we can do something different. So again, thank you very much. Appreciate it. Have a great, here in the U.S., we're celebrating Martin Luther King Day and our inauguration. So have a great day for those that have their day off, but jumped on the call. We appreciate it. So thanks a lot.
Thank you, Scott. Thanks, everyone.
Yep. Thanks.